Hi everyone, welcome to the series Blast from the Past from IMS. I'm Dr. Nishant Gupta, and in today's session, we'll be doing some of the questions of the modern math. So my suggestion is, guys, before you look at the solutions or the approach, you try all these questions on your own by pausing the video at every question. So let's start with the first question. Here the first question is, what is the number of distinct terms in the expansion of a plus b plus c raised to the power 20? This is a binomial expansion, and the general term of a binomial expansion is k some constant value into a raised to power p into b raised to power q into c raised to power r, where the sum of p, q, r is equal to a. In this case, 20. And this is nothing but the number of ways of distributing 20 identical articles among 3 different kids. Okay. So, whenever we want to distribute n identical articles among our different boxes or among our people, so we use the formula that is n plus r minus 1 c r minus 1. Here, we want to distribute it in 3 kids or in 3 different boxes. So, this is 20 plus 3 minus 1 c 3 minus 1, which is nothing but 22 c2, and 22 c2 is 22 into 21 upon 2 into 1. This gets cancelled. So 11 into 21 is 230. So number of distinct term in the expansion of this will be 230. This question says, the figure below shows the plan of a town. The streets are at right angle to each other. The rectangular park P is situated inside the town with the diagonal road running through it. So this is the park in which there is a diagonal road. Let's name these points M and N. So M and is a diagonal road along the path. Also, there is a prohibited region D in the town. So this is the area where you are not allowed to enter. Now Neelam rides her bicycle from her house at A to her office at B, taking the shortest path. So the number of possible shortest path that she can choose is, if Neelam wants to take the shortest path, she should travel from A to M and M to N and then N to B. This would be the shortest path because diagonal will be shortest in this case. Now, in order to reach from A to M, Neelam needs to take 2 turns in the east direction and 2 in the south direction. Now, it doesn't matter whether she is taking 2 east first and then 2 south turn later, or if she takes 2 south turn first and then 2 east. So, in how many ways can you arrange double E, double S? This is like arranging banana, statistics, mathematics, Mississippi. So this can be done in factorial 4 upon factorial 2 into factorial 2. And mean multiplication. In fundamental principle of counting, we discuss this concept. From M to N, the shortest path is 1. The diagonal is the shortest path here. So there is only one way to reach from M to N if you are following the shortest path. And then from N to N, B, from N to B, if you want to reach, then you need to take 1, 2, 3, and 4 east and 2 south turn. So if you want to take 4 east and 2 south, that means you need to arrange 6 articles, of which 4 are identical and 2 are identical. Now factorial 4 upon 2 factorial into 2 factorial is nothing E into 2 into 1 upon 2 into 2. 1 is as it is, and 6 factorial can be written as 6 into 5 into 4 factorial upon 4 factorial into 2. I'm writing 2 factorial as 2, that is 2 into 1. So this is 2 to the 4. So 6 cases, 1. Here factorial 4 gets cancelled. This is 2 3s are 6 and 5 3s are 50. So the total number of ways in this case would be 90. Now we have one more question on the same data. It says Neelam rides her bicycle from her house at A to the club at C. So from A to C, but the condition is via B. So Neelam first will go from A to B and then from B to C. The number of possible shortest path that she can choose is, we have already calculated the number of ways in which she can reach from A to B following the shortest path, and that is 90. So we will use that information in and mean multiplication. Now, in order to reach from B to C, there is a problem that some of the routes, if you start counting like this, as we counted for the other points, if we count that, then we'll be taking these routes also into consideration where it is prohibited to enter. So in that case, what do we do? If we construct these imaginary routes, so what is Neelam doing? When she is trying to reach from B to C, she is considering all the points if there is no restriction. But since there is a restriction, so all those routes which are going from B to C via D are not acceptable. So from B to C, we'll subtract those cases which will go from B to D and then D to C. So in how many ways one can reach from B to C if there is no restriction? See, one need to take 1, 2, 3, 4, 5, 6 north turn and 2 west, which means it is 8 factorial upon 6 factorial into 2 factorial minus from B to D. In order to reach from B to D, you need to take 1, 2, 3, 4 north turn and then 1 and 2 west turn, which you can take in factorial 6 upon factorial 4 into factorial 2 cases. Also, once you reach D, then there is only one way in which you can reach from D to C. That is the shortest way, a straight, direct route from D to C. So we need to subtract these cases. We are counting here all the routes, possible routes from B to C and subtracting all those routes which are going from B to C via D. So 8 factorial here can be written as 8 into 7 into 6 factorial upon 6 factorial into 2 minus 6 into 5 into 4 factorial upon 4 factorial into 2, and this into 1 we are not writing here, it is simple multiplication. So if we solve this, this is 15 factorial 6 gets cancelled, 2 4 the 8, so 4 7 the 28 minus 15. That means the number of ways in which Neelam can reach from B to C not taking these paths which are going via D, that is 30. In order to reach from A to C via B, the total number of paths will be the product of these. 19 to 13 is 1170. It says how many integers greater than 999 but not greater than 4000. Now understand, we want to make a number which is greater than 999, which means it should be at least a 4-digit number, because numbers greater than 999 are 1000 numbers, but not greater than 4000. Now here's the catch. You need to ask yourself, is 4000 included? Because they're asking you not to take the number more than 4000. That means 4,000 is acceptable. So we want to make the numbers between these two numbers. Okay, here 4,000 is acceptable. That can be formed with the digits 0, 1, 2, 3, 4 if repetition of the digit is allowed. Understand, whenever you want to make a 4-digit number, your number cannot start with 0. Even if it is 3-digit number or a 5-digit number, you cannot start it with 0. Okay, so I cannot place 0 at 1000 place. At the same time, if I use digit 4 at 1000 place, there is a problem. Because the moment you write 4 here, and if you write 1, 0, 0 or 4, 0, 0, 1, this will be more than 4,000. The only number which is acceptable in this range is nothing when you place 4 at 1000 place and you put other digit as 0, which is one case. This is one case. In all other cases, the digit at 1000 place can be 1 or 2 or 3. It cannot be 0, otherwise it will not be a 4-digit number. It cannot be 4, otherwise it will be more than 4,000, except this case. So the place, 1000 place can be filled in 3 different ways. And for the other places, there is no restriction because repetition of the digit is allowed. So we can put any of the 5 digits at any of the place, which means the 100th place can be filled in 5 ways, 10th place can be filled in 5 ways, and unit place can also be filled in 5. So in all, it will be 375 cases, okay, in which we are not counting this case yet. So we need to add one more case, that is 4,000. That is 4,000 because they are asking you not to take greater than 4,000, which means 4,000 is accepted. So the total number of cases in this case would be 370. Next question on your screen is, there are 6 tasks and 6 persons. Task 1 cannot be assigned to the person 1 or 2, and task 2 must be assigned to the person 3 or 4. Now, every person is to be assigned one task. In how many ways can the assignment be done? So let's understand it this way. If I write the task like this, let's say these are the 6 tasks: T1, T2, T3, T4, T5 and T6. As per the given conditions, we will follow the task 1 cannot be assigned to the person 1 or person 2. So I cannot assign this task to the person 1 or person 2. Now, most of the Janta makes a mistake here. That is, they say that task 1 here can be assigned in 4 ways. You need to read the other condition also that says task 2 must be assigned to the person 3 or 4. So I can assign the task 2 in only 2 ways, which is either I'll be assigning it to the person 3 or to the person 4. This can be done in 2 ways, which means one of the guy out of 3 and 4, person 3 or person 4, must be working on task 2. So for task 1, we don't have person 1, we don't have person 2 because it is said they cannot do this work. Out of 3 and 4, one will be working on task 2. So only remaining 3, out of remaining 3, one can do this work. So task 1 can be assigned in actually 3 ways. It cannot be assigned in 4 ways because one out of the remaining 4 guy will be working on task 2. Now, for task 3, 4, 5 and 6, there is no restriction. So there are 4 people, 4 tasks. Everyone needs to be assigned one task. So this can be done in 4 into 3 into 2 into 1 ways, which means 144. Hi. So there is another question. It says 3 Englishmen and 3 Frenchmen work for the same company. Each of them knows a secret not known to others. they need to exchange these secrets over person-to-person phone call so that eventually each person knows all 6 secrets. None of the Frenchmen knows English and only one Englishman knows French. What is the minimum number of phone calls needed for the above purpose? So here we need to minimize the number of phone calls to exchange all these secrets. Now let's assume the Frenchmen here are F1, F2 and F3. And let's assume the number of or the Englishmen are E1, E2 and E3. Let's say E1 is the guy who knows French. There is one English man who knows French. So we are assuming E1 knows French. Now, these are the persons F1. When F1 will call F2, they'll exchange their secret. So the secret known after first round of call will be F1 will know F1's secret and F2's secret. Here, F2 now knows the F1's secret when they have exchanged the calls and his own secret. Now, if F2 calls F3, so F2 will know the F3's secret also, and F2 will tell F3 the secret of F1, F2, and he also knows his secret. So he knows these 3 secrets. Now, if F3 calls E1, so here F3 will know E1's secret also during this call, and E1 will get to know the secret of F1, F2, F3, his own secret, and when he'll be calling E2, he will know the secret of E2 as well. Now, E2 will know the secret of F1, F2, F3, E1, E2 through E1, and when he will call E3, he'll know the secret of E3 as well. So basically, he'll know all 6 secrets. He knows all 6 secrets during this call. And when E2 will be calling E3, he'll also know all 6. So how many calls have they made so far? This is 1. This is 2. This is their third call. This is 4th. And this is 5th. So by the end of the 5th call, E2 and E3 already knows all 6 secrets. Now, either of E2 or E3 will call E1. Now, he'll also know all 6 secrets because whenever they will be exchanging their second call, they know all 6 secrets, so they'll be sharing it with E1. And E1 is the only guy who knows French, so only he can share it with the French people. So, this call, then E1 will be calling F3, then F3 will be calling F2, and then F2 will be calling F1, and that is how in the second round, this is the second round, everyone will know each other secret. This is the second. Okay. So, we have the number of call exchange will be 6, 7, 8 and 9. So, in minimum 9 calls, they can exchange all 6 secrets. Here's another question on your screen. Let S be the set of 5-digit numbers formed by digit 1, 2, 3, 4, 5 using each digit exactly once such that exactly 2 odd positions are occupied by the odd digits. So in this particular question, we have 5 distinct digits, 1, 2, 3, 4, 5, out of which odd digits are 1, 3, and 5, and even digits which are available are 2 and 4. Okay. Now we want to make a 5-digit number. We want to make a 5-digit number here such that exactly 2 odd positions are occupied by the odd digits. So see, this is a odd place, this is a even place, odd place, even place, odd place. How are we counting it? No, it is first position, second place, third place, fourth place, and this will be the fifth place. So we want out of first, third, and fifth, exactly at 2 positions, there should be 2 odd numbers. And at the third odd place, there should be an even digit. Now the question is, what is the sum of the digit in the rightmost position of the number? Now, sum of the digits in the rightmost position. Now here's the trick. They're not asking you to calculate the number of such numbers. They're asking you the sum of the digits at the unit place. Rightmost place is unit place. So we'll make cases here. So case one, when I want to make a 5-digit number and I want to keep the unit place as even, which means at first and third place, I need to keep an odd digit. Okay. How many even numbers do I have? 2 and 4. So either I'll place 2 here or I place 4 here. If I keep 2 here, I just need to check for how many cases 2 will stand here at unit place. So since it is a 5-digit number, so let's find the another 4 digits. Now in this case, we have 3 odd digits, out of which we need exactly 2 digits which can be used at first and third position now, because already at 5th position we have placed an even digit. So what we'll be doing here, we can fill this place with any of the 3 odd digits, which is 1, 3, 5. This can be done in 3 ways. And this place can be filled in 2 ways. The moment you do it, you have already filled 3 places out of 5 and you're left with 2 different digits, and there's no restriction for those digits. So you can fill the remaining 2 places in 2 into 1 ways. So for these many cases, this unit 2 will stand at unit place. This digit 2 will stand at unit place for these many cases. How many cases are these? 12 cases. For 12 cases, 2 will be there at the unit place. Same way, if you look at the case where you're placing 4 at unit place, that means you have already occupied one of the odd position with the even place, even digit. So what we'll be doing here, again, these 2 odd places can be filled with the remaining 3 digits in 3 into 2 ways. And for the remaining 2 positions or places, we have 2 digits and there's no restriction, which again can be done in 12 ways. So there will be 12 numbers in which the unit digit will be 2, and there will be 12 numbers in which the unit digit will be 4, which means this will give me 24. The sum will be 24 for these 12 numbers, and the sum of the unit digit for these 12 cases will be 48. This is case 1. Now case 2. What is case 2? If I don't use even digit at unit place. So let's say if I use even digit at third place, which is 100 place here, and I fill this place with an odd digit. So what are the options I have? I can put 1 here, I can put 3 here, I can put 5 here. These are the 3 odd digits available to me. Now, for the remaining 4 places, in how many ways can we fill these remaining places? Because the number of ways in which we can fill the remaining 4 places will be the number of cases where these units or these digits will stand at the unit place. So if I want to fill the third position with an even digit, this can be done in 2 ways. This can be done in 2 ways. Either I'll be putting 2 here or I'll be putting 4 here. Then this odd place I need to fill with the remaining odd numbers. How many remaining odd numbers are there? If I put 1 here, so I'm left with 3 and 5. So I can put any of the 2 digits here at this position. So this place can be filled in 2 ways. Now for the remaining 2 places, again I am left with 2 digits which I can arrange in 2 into 1 way. So for 8 cases, unit digit of the number will be 1. Same way, if you place 3 at the unit digit here, you will see that this place can be filled in 2 ways with the 2 even digits, 2 or 4. Here you can place the remaining 2 odd digits, and for the remaining 2 places there is no restriction. So again 8 cases. And for the unit digit 5, if you put 5 at the unit place, then again you will get same 8 cases. So in 8 cases, unit digit will be 1. So the sum will be 8. In the next 8 cases, unit digit will be 3. So sum of the unit digits will be 24. And in the remaining 8 cases, the unit digit will be 5 and sum of the digit will be 1. Okay. But there is one more case which we need to write here. So I'm writing that case here. Please pay attention. That case is case 3. That is, if you fill this first odd place with an even digit and the remaining 2 odd places with the odd digits. Again, if you put 1 here, then you'll be filling this place in 2 ways. You can fill this place in 2 ways. For the other places, there is no restriction, so you can fill it in 2 into 1 ways. Which means for 8 cases, 1 will be here at the unit place. Same way, if you place 3 here at unit place, then the number of cases in which this will happen is 8. And same way, if you place 5 at the unit place, then there will be 8 cases in which 5 will be at unit position. So these will give you same result as we got from here. That is 40 plus 24 plus 8 is 72. So the total number of cases here would be these 72 plus 72 plus these 70. That is 260. In a chess competition involving some boys and girls of a school, every student had to play exactly one game with every other student. So in order to play a chess game, you need 2 players. So the order here doesn't matter, it is a case of combination. It was found that in 45 games, both the players were girls. And in 190 games, both the players were boys. The number of games in which one player was a boy and the other was a girl is, let's assume that there are total G girls and there are total B boys. Now, the number of games in which both the players were girl were 45. So that means that is equal to number of ways of selecting two girls out of G girls is equal to 45. That is G into G minus 1 upon 2 equal to 45. Or I can also write this as G into G minus 1 equal to 90. G and G minus 1 are two consecutive numbers and the product is 90. So we can simply say that G is equal to 10 and this will be 10 minus 1. So the total number of girls were actually 10. Same way, we'll calculate the total number of boys. Now, if there are in all B boys, then the number of matches which can be conducted among boys only will be BC2, which as per the question is equal to 190. That means B into B minus 1 by 2 is 190, or B into B minus 1 is equal to 380. Again, B and B minus 1 are two consecutive numbers. So, that means the numbers are 20 and 90, which means initially there were 20 boys. Now, the question is, the number of games in which one player was a boy and the other was a girl. So, we need to select one girl and one boy, one girl and one boy. So, in how many ways we can select one girl out of 10? It is 10C1. In how many ways we can select one boy out of 20 boys? 20C1. That is 10 into 20. In all, there will be 200 games in which one of the player will be a boy and the other will be a girl. An intelligence agency formed a code of two distinct digits. It is a two distinct digit code selected from 0 to 9 such that the first digit of the code is non-zero. So you want to make a non-zero which is not starting with 0, a two-digit code not starting with 0 actually. So I can fill this place with any of the digits from 1 to 9. So this place can be filled in 9 ways. And for the unit place, now I can use 0. But since we want two distinct digits, so whichever digit I have used for 10 place cannot be used again. So for unit place, again we have got 9 options. So in all, we can create 81 distinct codes if there is no other condition. But the code handwritten on a slip can, however, potentially create confusion when read upside down. When it is read upside down, it can create confusion. How? For example, if it is 91, if you read upside down, it will appear as 1660. So, how many codes are there for which no such confusion can arise? The confusion will arise when you read the upside down digit and it will look exactly same or will like some other digit. So what are the digits which can create confusion here? Digit 1, digit 6, digit 8 and digit 9 here can create confusion. These are the 4 digits which can create confusion, because when you read these digits upside down, so 9 will be read as 6, 6 will be read as 9, sorry. These are the 4 digits which can create confusion. 9 can be read as 6, 6 can be read as 9, 1 can be read as 1, so reversing the order. So how many two-digit numbers can be formed using these 4 digits if repetition is not allowed? So we can create 4 into 3, 12 such numbers. So these 12 numbers are made with the digits which can create confusion. But again, there's a catch. What is that catch? A number 69 will never create any confusion for you, because when you read it upside down, it will still be read as 69 on. Same way, if you read a number 96 upside down, it will still look 96. So these two numbers will not create any confusion, and hence we are subtracting out of the pool of 12. So the remaining 10 codes which are made from these 4 digits will create confusion, and hence should be eliminated from the total number of cases. So the total number of distinct code which will not create any kind of confusion in this case will be 71. Consider the set Tn equal to n, n plus 1, n plus 2, n plus 3, n plus 4, where n equal to 1, 2, 3, 4 till 96. How many of these sets contain 6 or any integral multiple thereof? That is, any one of the number 6, 12, 18, 24 and so on. Let's plug in some values and try. If I put n equal to 1 and I calculate t1, so it will give me 1, 2, 3, 4, 5. Now, there is no number which is a multiple of 6. Out of these 5 numbers, there is no number which will be a multiple of 6. But the moment I put n equal to 2, so it will be t2, which is 2, 3, 4, 5 and 6. So we found one number which is a multiple of 6. Now if you put n equal to 3, it will be 3, 4, 5, 6, 7. Okay. Then if you put n equal to 4, it is 4, 5, 6, 7 and 8. Then if you put n equal to 5, it is 5, 6, 7, 8 and 9. And the moment you put equal to 6, it will be 6, 7, 8, 9 and 10. But now, when you try to put n equal to 7, the moment you put n equal to 7, it will be 7, 8, 9, 10, 11 and done. So there is no multiple of 6 now. So this way you can check the pattern that out of every 6 numbers, because 6 will start from here and it goes till here, out of every 6 sets, there will be 5 sets in which one of the number will be a multiple of 6 or multiple of 6. So in all there will be 96 such sets, because we are placing n equal to 1, 2, 3, 4, 5 till 96. So out of 96, if we make a group of 6, so we can create 16 groups, and in every group there are 5 sets which are multiple of 6. So basically it will be 6 by 5 or 5 by 6, which is equal to 8. Next question is here from the topic set theory. A survey on a sample of 25 new cars being sold at a local auto dealer was conducted to see which of the 3 popular options, AC, radio and power window, were already installed. So the survey is conducted over 25 cars. And since it is not mentioned that every car will have at least one of the 3, so it is basically a universal set. It may not be a union B union C till the time they mention it. Following were the observations of the survey. 15 had AC. So let's write AC, radio, AC, radio, and then power window. So 15 had AC. This is the complete set which contain AC. 2 had AC and power window, but no radio. AC and power window both, which means we are talking about this part. This is AC and power window, but no radio means this part we are talking about. So this is 2. Now, 12 had radio. So in all, 12 cars have radio. Then 6 had AC and radio, but no power window. AC and radio is this part. This is AC and radio, but since it doesn't have power window, which means we are talking about this area, and this is 6. 11 had power window. 4 had radio and power window. Now there is a slight catch. Earlier, what they were saying, the other had 2 of the 3, feature, but not the third one. Exactly 2 of the 3. But here they have said that 4 had radio and power window. So this 4 is this part. This denotes the number of cars which had radio and power window. 3 had all 3 options. So if it is 3, that means there's only 1 car which had only radio and power window, but not AC. In all, 15 cars have AC, of which we know about the 11 cars which have at least one other feature also. So which means the remaining 4 will have only AC. Same way, 12 cars have radio, out of which 10 have at least one other feature also. So the remaining 2 will have only radio. Out of 11 which have power window, 6 have at least one more feature, which means the remaining 5 will have only power window. Now the question is, what is the number of cars that had none of the option? So basically, the cars which have at least one of the 3 options are these cars. If we count this is A union B union C, which is equal to 15, that is AC, is the sum of this circle, plus this, and this. So these cars will have at least one of the 3. No? At least one of the 3 feature. In all, we surveyed 25 cars, out of which 23 have at least one feature. So the remaining 2 will have none. So there are 2 cars which have none of the option. Option 4 is the answer. A survey was conducted of 100 people to find out whether they had read recent issues of Golmaal, a monthly magazine. They summarized information regarding readership in 3 months is given below. Only September but not August, September and July, September, July and August. So they have given the data for the 3 months basically. So let's write down the value. So let's say this set represents to the July, August and September. Okay. So only September means this area. So there are 18 people, those who read only September issue. September but not August. September but not August, which means we are talking about this part. We are talking about this part. Okay. And we already know September but not August, this yellow part should be 23, whereas only September is 18, which means the number of people, those who are reading September and July but not August, will be 5. This must be 5 because the total is 23. September and July is 8. What is September and July? This part. This is 8, of which this is 5. So number of people reading all 3 should be 3. Then September is 28. Now the number of people reading September issue is 28, of which we know this 18 plus 5, 23. plus 3, 26. So the number of people, those who are reading only September and August, should be 2. Next information is July, 48. So there are 48 people, those who read July edition. July and August. July and August is this part. This part is July and August. This is 10. Out of which 3 are reading all. So that means there are 7, those who read only July and August. Next is none of the 3 is 24. So they surveyed 100 people, of which 24 are not reading anyone. That means the remaining 76 are reading at least one of the 3. Okay. That means, see, we also know this total of the July, of which we know that number of people, those who are reading at least one more edition with July, is 15. So if we subtract 15 out of 48, we'll get 33. And that is the number of people, those who are reading only July edition. It is also given that A union B union C here should be 76, which means sum of all these values, if you take this to be X, sum of all these values should be 76. Let's equate this. This is 28 plus X plus 7 plus 33 equal to 76. X plus 40 plus 28 is 68 equal to 76, and X equal to 76 minus 68 is equal to 8. So this value is 8. Now what is the number of surveyed people who read exactly 2 consecutive issues? This is a trick question. They are not asking you to calculate the number of people, those who read exactly 2 issues. In fact, they are asking you to calculate the number of people, those who read exactly 2 consecutive issues, which means either they read July, August or August, September. Anyone who is reading July, September are not the people, those who are reading 2 consecutive edition. Okay, so this will not be. So July, August is 7. This is 7. And August, September is 2. So the total number of people, those who are reading exactly 2 consecutive issues, is 9.